Okay, today I'm gonna have a little more about lists, and then we'll talk a bit about sets, and then start touching on sorted sets, and we'll continue that tomorrow and maybe a little bit beyond. Maybe you're wondering why all this? So in Python, we had an array, and you can just sort of do all this sort of stuff with that. And what I hope you're getting a sense of is that when you are storing data in an application, how you store that makes a difference. And so having a rich set of data structures to choose from when you're deciding how to store and organize the data that you have can make a big difference. And we'll see a little bit of an example of that, just in terms of choosing what type of list to have. So having a little bit of insight into the difference between array lists and linked lists. And then another little thing about lists, and this is true of actually all collections, not just lists, is that sometimes an array is a better way to have things, but sometimes we have it in a list, and then sometimes we want to use it as an array, or sometimes we have stuff in an array and we want to put it into a list or some other collection. So kind of why is that? One of the critical things about Java arrays, if you remember, is that they are fixed and that they have what's called, bounds checking. In other words, when in a Java array, if it's of a given size, you can't put any more into it. And so there's situations where you want to really enforce that. If you have any one of these collections and you accidentally put some more stuff in it that you don't want, then it'll go in. If there's an array and you try to put more stuff into it, then you'll get an exception for that. So sometimes you're in a situation where you're building up the data to a certain point, and then you want to kind of freeze it. And so an array is a better structure for freezing a fixed set of things. A collection is a better way to organize data where you don't know how many they're going to be. You want to be able to put them in, take them out, etc. And then we'll start taking a peek at sets. So that's okay. Just as a reminder, this is the overall organization. We're kind of on this branch here. We're going to spend a little bit more time talking about these, and then towards the end of today, and then continuing, we're then going to switch over to this branch and then take a look at that. And then when we're done with all of this, then we're going to move on to another type of thing that doesn't fit into this, called a map. So this is all review, but just to remind, if we have we can declare our list to be of a certain type, and then instantiate it, in this case, as one of the two types that we have out of the box. The other thing about this is that if for whatever reason there's some other way of organizing things, especially when it comes to sorting things, there are a bazillion different ways of actually implementing that under the hood. Java chose a particularly sophisticated one, but for a given application, sometimes there are other ones that might do a little bit better in that context. And so, because of this, you can, if you have a kick-ass algorithm for storing things in sorted order, and for whatever reason you don't like the Java one, you can implement your own. And in all places where you're using a sorted set, it can be used without any modification of that code. The other thing is, if you If you have an idea of how much you're going to be using, I actually don't use this too much because I found that the expanding is usually fine. But sometimes there are situations where you do want to specify the starting size. I don't even, I can't remember what the default starting size is, but for an array list, and you don't necessarily need to use this, know this to use array lists, but under the hood there is it uses an array, and then when you add things and it exceeds the size of that array, then it basically does what we did. We copy the array to a larger one and then start adding it. And then when that fills up, they copy it again. And I'm pretty sure they haven't, my recollection, I haven't looked at it in a while, but my recollection is they just kind of double the size of the array every time. No, but, all right. Okay, so now adding things, now to lists, there are actually a couple of ways of adding them. I rarely use this form, but it is a possibility. Basically, when you add it, it adds it to the end of the list. But we can add things at a particular index, and then what happens when we do that? Well, everybody with a bigger, everybody at that index and bigger shifts to the right. And likewise, if you remove for a given one, everybody shifts left. We've seen a little bit that. And of course, now the constraint here is that when you use this form, you need to know that the index has to be, oops, this is actually incorrect. This should be, it has to be strictly less because of the zero-based stuff. We talked about auto boxing, again, just to what's happening there. So if I have a list containing doubles, I can sort of add this. Java actually doesn't let you do this anymore. That's what we had to do back in the day. Now it's all deprecated because they said you never, now that Java does auto boxing, don't do that. Instead, just add the number, and underneath the hood, it will wrap that. You know, why is that useful? Because what that means is that the fact of only having the object wrappers as the contents now is not an impediment to actually manipulating the numbers. In other words, if we want to, well, in this case, just add a number, we add the number, and Java takes care of it under the hood. If we want to sort of get values and manipulate them, so for example, let's say we had a list of numbers and we wanted to find the average and the standard deviation of them, we wouldn't have to explicitly unwrap them, even though that's what we used to have. That's what we used to have to do, but we don't have to do it anymore. So it makes the code a lot cleaner and just easier to read, because all this new stuff just was getting in the way of the calculations, and it was a pain. People complained. The Java developers heard the complaints and said, okay, we can fix it. So that's, unfortunately, there's the dark side to that is that they put all kinds of stuff in Java that, in my opinion, is more, well, I won't go there. Oh, okay. So now here's the thing, is that this is, for a given list, we can remove a particular item. And so if I have a list of strings and I say remove, George, it'll go and try to find George and remove the first one. But or I can say remove 5, and so it'll find the guy at 5 and remove that one, regardless of what it is. So here, I need to know which item I'm removing. And for this, I can just say, yank the guy at this particular index. And if the index isn't viable, what does that mean? I mean, if I only have 5 items and I say remove the item at index 5, then It does the same thing as you would with an array. In other words, and this is why the zero-based indexing is so screwy. If I have 5 things, I say remove the 5th thing, there is no 5th thing, so I'll get an exception. Was there a question? Yeah.
Yes, sir. So is this like add where it shifts, elements shift, I guess?
Yes. Yeah. So when I remove at a given index, everybody, or if I remove that item, everybody shifts. And that's what, for an array, conceptually that's what happens. So for an array list, what that means is that everybody, you have to sort of, you go here, it's kind of like the, the time at Valley Forge where George Washington addressed the troops, and he says, I've got good news and bad news. The good news is that you're going to get a change of underwear. And the bad news is you change with you. So, let's see. Wait, do I want to do this? Let's see. Okay, I'll do it. Yeah. Now, we've seen the for each syntax with arrays, and the same syntax works with lists and with all collections. So this will work for both lists and for sets. And that, it's a for, it says for each, but basically you're saying, okay, for each string in this list, assuming the list contains strings, and if we want to loop over the whole thing in order, then this is a nice way to do it. If we don't care about the index, if we do care about the index, then we have to use, we can use an indexed one, but a better way is to use an iterator. And so there is every collection can produce something called an iterator. And an iterator is an object that, iterates through it. Now with a list, it iterates by going in index order, starting with the 0th element and up. It's also, because sets also have this, and because sets don't have a concept of an index, this is actually, this is almost the only way to kind of iterate through a set, which we'll talk about next. So what is an iterator? An iterator has basically 2 methods. One is next, and next does what you think it does. Next just sort of points to the next thing. And then the other is a Boolean has next. We've seen a little bit an example of this with scanner. So scanner is an iterator-like thing. There, of course, they had there it actually did have a next, and the next gave the next string, but it also had the scanner had next int, next double, et cetera, et cetera. And then there were various, has next line, has next int, and stuff like that. But in iterator, it's just these 2. An iterator, as you notice, it is generic because, and that allows you to have type safety with this. Again, if you're removing from, if the task is, I want to go through a list or any collection. This works for all the collections. Let's say I want to remove one or more items based upon a certain criterion. And I don't know where that is. So that's the problem with, if I want to remove the item, let's say I wanted to remove every item. And I don't know where they are though. Why? Because they've been put in some kind of weird order. Well, this is pretty much for lists there's an alternate way, but this is a preferred way of doing it because this works with sets as well. So using an iterator has the ability to remove something that preserves what's going on under the hood. If you iterate through the, you would think that, okay, if I just kind of loop over this and say, well, if the string is equal to the one I want to yank out, then remove it inside here. But that doesn't work. And the reason it doesn't work is because when you're looping over one of these collections, it needs to maintain its integrity. So think of an array. Let's say you're iterating over an array and you want to remove, let's say an array of strings, and you want to remove all the ones that start with, the letter T, let's just say. So a string can let you know which one that is. If you're doing it over an array, and then now you can actually, in an array list, remember, if you remove that, then everybody kind of shifts over. But if you're indexing, your loop would carry on and move to the next index. And so if you had two of them in a row, you'd miss one. So and Java doesn't let you do that. It doesn't let you change the list or the collection as you're iterating it over. But it lets an iterator do that, because the iterator has code that sort of keeps everything straight. So when we talk about sets, I'll show you how to do that. And then this is something I've never really used, but I can think of one instance in the past 25 years where this has come a little bit handy, but there's always another. But a list iterator is a special type of iterator that works only on lists, but it can go forwards and backwards. A regular iterator only goes forwards. So we'll see an example of that, if not today, then when we talk about sets, the iterator thing becomes more useful. Okay, remember I said it's important to choose the right data structure for your program. And here's a show you a little bit of an example. Just if you're organizing things as a list, if you're putting stuff in and taking stuff out, then an array is not an ideal structure. Why? Because they're even if you say, okay, I'm going to make an array bigger than any amount of data that I'm ever going to use. And Murphy's Law says that you're going to need one more than that. Now back in the day, when PCs first came out, and I think this was Gates who was kind of, the first PCs had 64 kilobytes of RAM. That's kilobytes. Why? Well, because at the time, Gates said, 32 kilobytes is the most that any program would ever need. But just to make sure that, that there's always going to be enough, I'm going to double it. So 64 kilobytes, that's kilobytes, that's, all right. Now we have 64 gigabytes. So basically, how did that work for you? So Murphy's Law says if you think that you're never going to have more than a certain amount, then you are. I might have shared this. The very first hard drive I bought, I was debating between 10 megabytes and 20 megabyte. Now we're in megabyte territory. Forget this kilobyte stuff. So 10 megabytes or 20 megabytes, and I went with 20 megabytes because I'd never have to buy another hard drive again. So again, how'd that work for you? They haven't repealed Moore's Law, evidently. Okay, so array list versus linked list. So the items underneath the array list are as arrays. It's resized if it's reached. You have constant time adding and removing at the end, but big O(n), where n is the number of items in it if you add or remove at the beginning. Are you familiar with the Big O sort of stuff? I mean, probably, yeah. So, and, you know, that may seem kind of theoretical and everything, but it where are we here? Okay, so in here, I didn't want to write it in front. I could have written it in front of you, but I, you know, just want to make sure I didn't screw it up too much. All right, so let's just sort of look at that. Here's the task at hand. You know, for whatever reason, it's a little bit artificial, but this is the kind of thing that, you know, that might be an issue. All right, so here I'm going to generate a million of these. I'm going to generate a million random integers. And first I'm going to put it into a linked list. So here I'm going to put in, I don't care about the actual numbers, so that they can just be anything. I'm fine with that. And then here what I'm going to do is I'm going to loop over the list, and while it's not empty, I'm going to remove the 0th index. Now, I can't do this kind of thing with a set, but I can do it with a list. And I want to figure out, I want to time it. So here's a way to time things. The system class has a method called current time millis. What do you suppose that tells you? What the current time is in milliseconds, which, depending on which platform you're on, in a Unix-based platform like Mac or Linux, it's the number of milliseconds since, I think, January 1st, 1970. And on Windows, it's since January 1st, 1980, maybe. It's kind of when they sort of brought that operating system online. Anyway, so, but regardless, we don't care about the absolute time, we care about the elapsed time. So before I do this action, I save the time, and then when I'm done with it, I'll get the time again. The difference is the amount that's lapsed, and I'll print that out. Okay, now I'm going to do the same thing for an array list. And okay, I got lazy, I didn't want to define a new one, so now I'm just going to take my guy, instantiate a new empty array list. See, I can do that because I've declared the list variable to be a list. If I said linked list, then I'd have to declare another variable, but I was lazy. I wanted to save the number of variables or something. Okay, so add some more. I'm going to do the same thing. So now my start time is going to be the current time here, and while that list is not empty, I'm going to remove it. So actually, here's another method that all collections have, and it's called isEmpty. And what do you suppose it does? Yeah, it returns a Boolean, and if the thing is empty, it's true. If it's got stuff in it, it's false. So, you know, the night, you know, naming your variables and your methods, you know, it should be as self-documenting as possible. I mean, there's no such thing as a 100% self-documenting stuff, but it's like, and you want to make sure that it actually does what it promises. So this method promises to tell me true if it's empty and false if it's not. So I say, well, it's not empty, I'm going to remove the 0th element here. For, you know, I say, well, okay, they're both lists. It's sort of a reasonable thing, so let's see what happens when I run this. So it took well, in this case, you know, usually it takes around 1/100 of a second to, you know, so since these are milliseconds, I'm multiplying it by 1/1000th to turn it into seconds. And we're still working on the array list. Either that or it's hung up somewhere. You got to be careful if you have one of the dangers of a while loop is that if you're not careful to be changing the status of the Boolean test within the loop, then you'll be there forever. And so, you know, you're seeing the blinking cursor, nothing much is happening. So maybe it got stuck. I don't think so. Okay, so it finally finished. Okay, so the time to do the same task for the array list was 53 seconds in this versus 1/100th of a second, okay? Now, if you're writing an application and you have two ways of doing a task and one of them takes 100th of a second and the other takes almost a minute, which one do you want to do? And, in other words, this thing about, okay, these two lists have different qualities, even though they both are the same kind of thing. For certain tasks, one is better than the other. I mean, just even in this sort of staring at that blinking thing, it's like, is the program hung up somewhere? Is it actually working? In fact, I was actually a little surprised at how long it was taking. So when I was first staring at the blinking thing, it was sort of taking forever. I didn't think it was going to be honest, I didn't think it was going to be quite this much of a disparity. So I actually kind of put little print statements in there to say, hey, every 1,000th one, I say, hey, I'm here. And darn it was there. It just kind of took forever. So, I mean, this is a real thing. I mean, and it really makes a difference. So I'm not just kind of blowing smoke up at you. Okay. Now, the other thing is that, sometimes we have, sometimes it's convenient to have things as an expandable structure, like a list, and sometimes it's helpful to have things as an array. And so can we convert one to another? And the answer is yes. And you think, well, how you could do this by hand fairly easily. How? Because every collection has a size, so I could instantiate an array of that size, loop through, copy every element into the right index. That's a lot of, that's a lot of stuff to do something which should be fairly straightforward. So instead, every collection has a method called toArray, which does what you think it does. But there are a few little caveats here. First of all, there are two versions of toArray. The one that's not terribly useful has zero arguments and returns an array of objects, which is usually useless, because if I want to do something with these numbers as integers, then an array of objects means I have to cast them, and then casting is always a bit dangerous. So instead, and now this was, unfortunately, I think what they did was they implemented this before they had generics. It would be, I'm not sure why they haven't done this with generics, but they haven't. What you do is, and this is kind of, you give it sort of a template of the type of array you want it to be in. And of course, it has to be consistent with what you've declared. In other words, if this list contains integers, then this array has to be the same thing, which to me says that they could have been able to do this. They should have been able to do this using generics, but they didn't. So this is kind of how you do that. Now, the caveat, the catch is we cannot directly create an primitive int array. Because everything is objects, and an int array and an integer array are completely incompatible. They're two entirely different objects. So I can't, you think, well, maybe I could take this and cast it to an array of primitive ints. That makes sense, and you can't. But here's how that works, and you can actually kind of go the other way as well. So there's another thing in here, and if you're pulling the code, you can sort of look at it. So here, just deal with just a small thing. So here, just have some 5 values in an array list. This will work for bigger things as well, but just for an example. So I'm just going to populate this with some random doubles and just sort of print what I get. So here's how I can turn that into an array of doubles, capital D. So these values, which were declared to be a double, there has to be a match between that and this, this right here. Notice I'm giving it a a zero size array because under the hood it does some stuff to make it the right size and everything. So this is just to emphasize the fact that I don't have to tell it how big to make the array. It can figure that out. So now it's an array, and so I can use, how do you print arrays? Just print as gobbledygook, but I can use the arrays toString to print that out. And then you might ask, well, what if I have an array and I want to turn that into, say, a list? Well, it turns out that there's the arrays, the same arrays class has another method called asList. And so if I give it an array, it will create a list. It will return a list of containing the contents of that array. And what's nice about this is that this is it's basically turning what would ordinarily be a complex operation, and taking the data from one type of content, one type of structure, and turning it into another, and it just basically makes it just like one line. And so I can, now if I print it, it should print the same stuff. The caveat, though, is the list that it returns is immutable. So how did it do that? It does it by the add and remove methods of the particular list that it returns, throw an unsupported operation exception. So for example, let's say if I want to add another number to that list, I'm going to get an exception. So let's see what that's about. Okay, as promised. So all right, here's the original list. This is the array that I printed here, and then this is the list that I got from the array back again. But when I tried to add a new number, notice I get an unsupported operation exception. So why is that? Because they returned an array list, or an implementation of list that you couldn't modify. Why do that? I'm sure there's a reason for that, but and we can see that was the problem right there. So let's undo that. So what if I have an array, I want to turn it into a list, but then I want to manipulate that. I want to maybe add stuff or remove something from it. Well, what I can do is then I can create a new one. And remember that one of the overloaded constructors of all collections is if I give it one type of collection, then it will take the contents of that and put them into this. So now if I now here this is kind of back with basic computer assignment expressions on that. So here I'm taking the contents of this immutable array, passing it to the constructor of this new array list. It'll copy all that in there, and then I'm going to assign that back to the original one. This is anyway. So now I can add this guy, and there he is. Okay. So what's the lesson? Is that it's very easy to move between arrays and lists and back again. And this is also true of sets. Sets have these same methods, and so that's particularly useful at times, because sometimes I want to use something like an array, and sometimes I want to treat it more like a set. Okay, so there, yeah, there's the. Okay, now as we've seen, as with arrays, if I have an array of something, there is nothing to prevent duplicates. So if I have, whether it's a string or a number, it just, whatever the contents of a particular index are, that's just what it is. And if I have duplicates, then so be it. The set interface is, one of its rules is it cannot contain duplicates. Okay, so that, and that introduces some issues. Why this thing keeps, there is no concept of an index with a set. So you cannot, well, with the exception of an ordered set or a linked hash set, and even there, there's really no concept of order. In array lists, or in all lists, there's a concept of order by index. The index is the order. In a set, it's like, if I add them in a particular way, and we'll see this when we'll look at the main implementation, which is a hash set. The order is, I mean, it looks arbitrary. It can look random, and you can't count on a particular order when you have a hash set. Now, there is a thing called a linked hash set. I think every once in a blue moon, I find that to be useful. But just in terms of a plain old set, the hash set is the workhorse on that. Okay, this is a sorted set, but let me, and I don't have to do this in front of you. So let's, all right, so let's, I mean, imagine, if you remember, we took our cards and we had a poker game where we're dealing out 5 cards, and that works fine if we're just kind of playing a game where the 5 cards is all you get. But in most of the poker games, that's kind of not the case. And that would, if we're doing like draw poker, we may have 5, but we may have, we may get more cards. That's a possibility. So the array of length 5 that we had there isn't quite going to cut it. So what would be better if we don't know if we're going to have 5, 6, or 7 cards? Well, maybe a set might work. Let's try that. So just for illustration, so let's see. I'll just sort of test the set here. And do I have? Oh, drat. Drat, I forgot to commit it. Let me. All right, so here's a playing card, not commented, so kind of just to make it happen. All right, so what I want to do is let's go back to here. I want a set of playing cards. Yeah, what was happening? Oops, ARDS. How about cards? All right. Let's just put the spades in. Let's see. Is it values or value? Value. Okay, so oops. All right, so okay, now something to notice here. Look at the order here. I put them in one value at a time, going from ace to whatever, but it stored them in a completely different order. Okay, why? Well, it's called a hash set. Why is it called a hash set? Because it uses something called a hash code to put the things into buckets and whatever. And if this were a class in data structures that you'd all have to be taking back in the day, then you'd kind of go into that and see what's going on. But we're going to have to, for a situation like this, we're going to have to kind of worry about it a little bit. Why? Because here's what I'm going to do. I'm going to add I'm going to add another ace of spades to my cards. Now, if you're playing here, I mean, a normal deck does not have two ace of spades. All right, so, and remember, a set does not contain duplicates. So I want this set, if I want to say, okay, I'm going to try to add another ace of spades, but if I already have one, then it shouldn't add it. But let's see what it does. All of a sudden, I have two ace of spades. And what the heck is with that? Because that's not how sets work. Okay, so why are there two ace of spades? Exactly. They're two different objects. So I need to do something to convince the set that if I have two objects that are different but have the same suit and the same value, then they're really the same card. But I haven't told Java that. As far as Java is concerned, hey, you just have two different objects. These are two different objects. You added another one, and it's not on my list. I mean, it's not in this set. That second ace of spades is not in the set. How can I fix that? Well, I need to fix that by overriding the equals method and the hash code method. So these are two methods. And unfortunately, it would be nice if this were also generic. But equals, and we've seen equals in strings. Remember how we had to use equals to compare two strings? And this is why, because if we had two strings, same characters, different objects. Although, as you saw, sometimes they're the same object, but you can't count on that. So now I want to say, if I have two playing cards, and they both have the same suit and the same value, as far as I'm concerned, they're going to be equal. Now, unfortunately, since the signature is an object, I may accidentally call this on something that's not a playing card. So what I might want to do is if you remember, there's let's say here not equals Okay, so if I'm trying to say if something that's other than a playing card is equal, otherwise, and, okay, so now, this is why I wish it was, okay, so I'm going to cast this object. I have to do that, again, this equals method has been there since version 1.0, and it had an argument of object because they didn't have generics back then, and so they just haven't updated it, but that's, and then now I can say, well, I want to use the getter, the and other card get value is equal to this get value. Okay, so now I'm almost there. This will not quite get me there, but let's see. Maybe that'll work. It won't. I know it won't work, but let's try it again. So let's run this, and all of a sudden we still have 2 ace of spades in our hash set. Why is that? Well, because the hash set uses the hash code to decide if 2 things are equal or not. And so what I need to do is I need to create a hash code that will be the same for any 2 cards that have the same suit and the same value. Now, back in the day, this used to be kind of a pain, but NetBeans has a nice way of doing it. So if I say generate missing hash code, and the principle is whenever you override equals, you also should override hash code as well. And so what you want to do is you want to pick, if there were more instance variables, you want to pick final instance variables for your hash code because you don't want that to be changing. So suit and value are always going to be the same. I'm going to generate it. It's it's fairly straightforward. That they just sort of pick the number and then multiply it by the hash code of the suit and the hash code of the value. Because these are immutable, this is always going to give the same number. So if I have 2 different playing card objects that have the same suit and the same value, this computation is going to be exactly the same. And so now I only have 1 ace of spades here. Why? Because it was using this to decide if 2 things were equal or not. And the reason it's called a hash set is because it uses a hash function, of which the hash code is an example. It uses a hash function to kind of put these things into bins and store them it's a very optimized way of storing things. So if I don't care about the order, but I want to make sure that I don't have any duplicates, then this is the way to do it. Now, if I'm using, in the case of object wrappers, like integers, doubles, etc., those all have are kind of the same. If I have 2 different integer objects that are both the same value, then they both have the same hash code because the hash code is based upon that value. Likewise, as we've seen for strings, it's the same thing. If I have 2 strings that are the same string in terms of characters, as far as the hash code and the equals goes, they are the same. And so if the utility of that, which we'll have to see tomorrow, is that if I have, say, a set of strings and I want to kind of match another string, chances are the string I'm trying to match is going to be a different object, but if it has the same characters, then it will do that. But here, let's see, if I want to remove, so let's say, let's say if I want another spade and, let's say the queen of spades. Now, if I remove the queen, now this is a completely different object, but now because they're matched and equals and in the hash code, here, let me make sure okay, so here I'm removing the queen, and as you can see, she's not there, whereas here, there she was at first. And then, now, the other thing to notice that when, let's see, did it rehash? Okay, it didn't, oops, removing. Now, it didn't do it this time, but sometimes if you manipulate a set, it'll kind of rehash things, and so the order may change. So again, the order in a set, you can't rely on that. It's just a bag of stuff. But the stuff has no duplicates, and you need to make sure that you have identified what a duplicate means. Okay, we'll talk about sorted sets tomorrow.